Hey gang, so we're on the topic increasing and decreasing functions. Alright, so here's our key concepts. We're going to identify points where the graph of the function has turning points. So you can see turning points, like it turns here, it comes down here, and then it turns and starts going up, and then it turns there. This is going to help us use algebraic methods to find optimum values of certain expressions. For example, the minimum surface area in a container of fixed volume. That would be lots of application in this. All right, so here's the idea. Suppose you have this function here. Okay, I drew it on here for you guys so you can kind of see it. So what I want to know is, when is the slope of this, what's the slope of this line doing? So let's write that here. I'm going to put it over here in black. Let's say, what is the slope, and we're talking about the slope of the tangent during this, doing from left to right. Because remember, when we're reading a graph, we always read it from the left to the right. From the left to right. All right, I'm going to go ahead and underline that. What is the slope doing? So let's think about this as we look at the slope of the tangent. So as we're going up this way, what would the slope of the tangent line be doing? Well, the slope it'd be a positive slope, right? Oh, my hand's kind of broad. The slope would be increasing. Or I really just want to say the slope on this right here would be positive. I don't really care what the slope is, but the slope is going up and up and up. And then it hits about right here. We'll call that point right there. And at that point right there, the slope is at a maximum, right? As we come up, we're at the maximum at the top of that function. And the slope of the tangent line right here would be 0. And then as it comes back down, my slope's going down, the function is decreasing. And so my slope, as the function's decreasing, what would my tangent line be? The slope would be negative, right? It would be negative. So, I mean, it kind of makes sense. If I were to draw a tangent line, the slope would be positive. And then when I go right here, the slope would be 0 because it'd be a horizontal line. And then as the slope starts going, as the function is decreasing, the slope of the tangent would be negative until it reaches about right here. And then what happens right here? At that point right there, oh, the slope's going to be 0 again. Right there, the slope would also be 0 again. And then my function starts increasing again. So my function is increasing. And so right here, my slope is going to be positive because my function's increasing. And then what happens here? My slope right here would still be 0 because it's a constant. That's a constant right there. The y value, the function, is just at a flat line. It's just at a constant, steady rate. So my slope would be 0. So let's give these names. Let's call this A, B, C, and D right there. So here's what I want you to do. I want you to look at my function that we've done. And I want you to say what interval, on the x interval, what interval is it increasing and what interval is it decreasing? I'm going to give you a second to think about that. All right. So when I talk about it's increasing from the interval A to B, and I'm going to do the open interval, from A to B, I would say my function is increasing. What about from B to C? It's going down, so I would say from B to C, it's decreasing. But then from C to D, it's going up again. So from C to D, it is increasing. So if I think about this, from A all the way to B, I have a positive slope. I'm going to put that over here, actually. I'm going to say A all the way to b, I have a positive slope. Meaning, what does that mean? If I have a positive slope, that means the function is increasing. I'm going to put that too. So when you go back to look at your notes, you'll have these words, meaning the function is increasing. Positive slope. If my slope is positive, the function is going up. Now, we're going to do a table down here, and it's going to kind of help you see this. So on this, put it in green. I'm going to say a positive slope goes up. Positive slope goes up. The function, meaning this function's going up. Decreasing or negative slope goes down. Decreasing. Negative slope will be a decreasing function. Okay, so you know, or hopefully you know where I'm going with this. We're increasing, decreasing, increasing, constant. The slope, the derivative, the slope of the curve would be a positive. If I have a positive slope, that would mean it's bigger than 0, right? If I'm decreasing, I would have a negative slope. Negative slope would be less than 0. So my slope of the tangent would be bigger than 0. Right here it would equal 0. Then it would be less than 0. And then it would be 0. And then it would be more than 0. And then it would equal 0. So let's give you a guide. The derivative guide. Oh, that looks kind of blurry. Let me see if I can focus in a little bit. Yeah, that's a little better. Okay, their derivative guide on interval AB. We'll just call it interval AB. Okay, and it's what I just said. If f prime of x, if the derivative is bigger than 0, if the slope is bigger than 0, the function is increasing. Function is increasing. If f prime of x is less than 0, if it's less than 0, the function is decreasing. All right, if f prime of x equals 0, that's the last scenario, like right here, then we know that the function is constant. Or it doesn't say this right here, but you might think of it as a turning point. In fact, I think I'm going to put that. Function is constant or a turning point. Because right here it hits 0 and then it turns and goes the other direction. So it's either means it's a constant like this right here, or it's a turning point. A max or a min. You could think of it like that. Okay, so I want to put over here, if f prime of x is bigger than 0, then the function is increasing and the slope is positive and the graph is going up. If f prime of x is less than 0, the graph is decreasing, the slope is negative, and the graph is going down. Okay? Keep that in mind as we are looking at these next problems. All right, most of these are straight out of Cognity. So we're just going to kind of go with them. Okay, so for a function f, you are given that f prime of x equals x plus 1 times x minus 3. Identify the intervals where f is increasing and where it's decreasing. Find the x-coordinate of the turning points of the graph, and graph a possible function f on the graph below. Okay, lots of information there. Let me see if I can adjust my camera just a little bit. Try and get that a little better. Yeah, that'll work. Okay, I am going to use lots of highlighters today. And you have to think about this because this will somewhat throw you off. It did the first time I did it, and I was like, wait, what? I'm going to give you the derivative. This is the function of the derivative. If f prime of x is bigger than 0. So if this function is bigger than 0, well, it's bigger than 0 here, and it's bigger than 0 here. Okay, because here's 0, it's bigger than 0, and it's bigger than 0. This down here is less than 0. And then at this point right here, and at this point right here, that's when we're at 0. The slope would actually be 0. There's my 0. It would be 0. Those are my turning points. And it's a little bit different from what you're probably used to seeing. Because you're used to doing graphs and being like, oh, well, this is increasing. Oh, wait, what? Isn't it increasing from here up? No. Think about it. This is the derivative. So you're looking for when are you above the x-axis and when are you below. All right, so let's look at the interval. So we're just looking from right here and up. When are we positive? Well, this is f prime of x, so we're positive up here. So I would say from negative infinity to negative 1, I am positive. If f prime of x is bigger than 0, the function is increasing. So this would be increasing. Okay, but then this happens, and we get low. F prime of x is less than 0. So that means from negative 1 to 3, we are decreasing. The function is decreasing. And then at 3 to positive infinity, we're increasing again. All right, find the x-coordinate of the turning points of the graph. Well, the x-coordinates are going to be right here. I'm just going to circle them. And right here. Those are the x-coordinates where we have our turning points. So it wants us to sketch a possible graph. Everybody's could be different. Turning points are at negative 1 and 1, 2, 3. I'm going to put this here. The reason I put these lines, they help me graph. Here's what I know. I know that over here at negative 1, I have a turning point, and at 3, I have a turning point. It does not mean that those are zeros. It's just a turning point. So I'm going to put this right here, and I'm going to say, okay, my graph is going up, 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 up at negative 1. But at negative 1, it hits a turning point, and it starts going down. And then maybe it hits the line here at 3, and what happens? It turns again, and it starts going up, up, up to forever. My graph could look something like that. It could be something different. It could be going up to here, and then turn and come down, and then go back up. All our graphs are going to look similar to this. They just might not look exactly like that. This is increasing. I'm going to use a pink. This is the graph is increasing, and then the graph is decreasing, and then the graph is increasing. And if you look, pink, yellow, pink, pink, yellow, pink, it follows that guideline. Okay, so that was increasing, decreasing. We graphed it. Let's take a look at the next one. All right, example 24. So the diagram below shows the graph of y equals f prime of x. Which value is larger, f of 0 or f of 1? Which value is larger, f of 1 or f of 4? Which value is larger, f of 4 or f of 5? Draw a possible sketch of the graph. Okay, let's just do exactly what we did last time. Remember, this is the derivative. So you're looking, when is the derivative positive? Well, it's positive here and here. And the derivative is negative here to here. And we have turning points right here at 1 and 4. I'm going to go ahead and just label it. I'm going to say that negative infinity to positive 1, it's increasing because it's positive. And then from 1 to 4, my graph is decreasing. And then from 4 to positive infinity, my graph is increasing again. Okay, so now let's look at this. Which is bigger, f of 0 or f of 1? And you have to kind of think of it. And maybe we should graph. Let's graph it first. I know turning points are here. I'm just going to graph it right here on this. Turning points are at 1 and 4. And again, it should hold true, so we should be able to do it. From negative infinity to 1, it's increasing. So I'm just going to put a point up here. It doesn't matter where. I know that as it comes up to 1 right here, it's increasing. And then at 1, it starts decreasing down. I'll just say down to here. Decreasing to 4. And then at 4, it starts increasing again. So I'm going to grab my red. I'm going to put it on here. F of 0. When x is 0, right here, or f of 1. Here's 1. Which is bigger, f of 0 or f of 1? F of 1. Which value is larger, f of 1 or f of 4? Here's 4. F of 4 would be down here. F of 1 is up here. Which is bigger? F of 1. Which value is larger, f of 4 or f of 5? F of 5 is bigger. And we already sketched our graph. Go back and watch that if you need to. Okay, example 25. Assume that the caffeine content in milligrams of blood of a certain person T hours after drinking a cup of coffee is modeled by C of T. Here's C. Oh, that is a pretty function. Okay, the rate of change of caffeine in the blood in milligrams per hour in this person is given by this. So the rate of change, meaning you could think of it as the instantaneous velocity or just the slope, the derivative, whichever one that you want to call it. But the rate of change, our slope, is this right here, this function. Find how fast the caffeine level is changing initially. Describe the change of caffeine level in the blood. How long does it take for the caffeine level to reach its peak? Okay. First thing I'm going to do is I'm going to sketch me a graph. I have no idea what this is going to look like. So, all the E's and everything. So, I'm going to have to go to my calculator. And I'm going to have to sketch the graph of this. And it's probably going to take me a minute to put it in my calculator. While you guys put it in, I'm going to put it into 614.95. I'll stop. Nope, I'm sorry, that's not how to stop. 614.95 times E to negative 2.5, nope, 2.1 x. Okay, I think that's right. I'm going to double check. 614.95e negative 2.1x minus 36.75e to the negative 15x. Okay, I'm going to graph it. My goodness, that's a rough one. Oh, there it is. Okay, I can tell that it kind of drops down there. I'm going to do zoom fit, do number 6. Just so I can see if I can see this. Oh. Okay, it looks like it goes down and then it comes back up. Right? So I don't really know what it's doing. I mean, I could do a window on this. I know that on the y-axis it's going down quite a bit, so maybe I go down. Let me just look at the table real quick. Oh my goodness, I think I'm still at table set 0.1. Let's do table set 10. Okay. Oh, it's not going down very far. I'm here at 64. Let me go to 1. I didn't know I was way off there. There we go. Okay, so it's dipping down, and then it's coming back up to 0. Okay, so it's not really going down that far. Maybe 10, 43, and then back up. So I'm going to do windows. Nope. Table set, no, window. There we go. I'm on the Y, I'm going to go down to like negative 50. I think that'll be good. Let's see what it looks like. Yeah, there it is. So it looks like it comes down, and I could, if I wanted to see just a little bit more, I could make the top part here, I could take that up to 50. I could see it a little bit better. So there it is. So I kind of get the idea of what it looks like. If you haven't played with your Windows tab that much, it's a good idea to kind of think about playing with it a little bit. Okay, remember this is the graph of the derivative. Not the graph of the function, but the derivative. The derivative is positive to right there, and then it has a turning point, and then it is all negative down here. And it didn't look like to me like it hit this line and it had an asymptote right here. Just got real close. So I want to know, what's that turning point right there? Do I need to know that turning point? Is it important to know that turning point? Find how fast the caffeine level is changing initially. Initially would imply right here. Like apparently it probably comes through and I didn't really. Well, I should have done that. Should have looked something like that. Okay, I know it didn't look that curvy, but anyway. Okay, so I kind of need to know where it's 0. Let me go back here. Look at there. When x is 0, initially it starts at 578.2. How do I know initially was 0? Because that's your starting point. You can't start at -1. You have to start at 0. So 578.2. So let's do when we plug in 0 into that function, we get 578.2. We didn't really plug it in. We just know that that's the y-intercept. Describe the change of caffeine level in the blood. Okay, so we're going to go from 578.2 to, what was that point right there? Did we find that point yet? Because for all the way from 578 to this point, I would say it's increasing. Right? It's a positive. And then what happens at that point? We reach the peak amount of caffeine in our blood, and then we start coming back down. So maybe you drink your energy drink and you are feeling good, and then a couple hours later, bam, you start coming down off of that caffeine drink. So what is that moment right there? That would be when x is, what is x right there? Well, what is y right there? You know y is 0. So let's go back to our graph. Let's calculate the 0 or the x-intercept, whichever way you want to do it. Second, calculate. Let's calculate the 0. That's the easiest way to think of that. Let me find my... There it is. You want to go just above it and hit enter. Move down below it and hit enter. And it says guess. And I say yes. I hit enter again. There it is. The 0 is at 1.4448219. That is not what I got the first time I did this. I got 1.19 last time. Okay, I probably need to make sure I got it in here right. Okay. 61495E negative 2. Oh, y'all, that's what happened. Do y'all see what I did? I didn't have it in there right. Okay, I'm going to go right here. I'm going to go second, insert 5. 5, 1. There we go. Okay. Graph it again. Oh my goodness. It's not going to actually throw off because my y-intercept was right. So I'm going to go back to second table. Y'all may have caught that. So that didn't change. But it is going to change when I go back to my graph. I'm going to do my y-intercept, or my 0 again. Second, calculate the 0. Okay, enter. I'm going to go below it. Enter, enter. There it is. 1.193814, blah, blah, whatever. So, I'm going to do 3 sig figs. 1.19. So, that point right there, 1.19. And the y is 0 right there. All right, so at 1.9, we have a turning point. And what happens at 1.19 to positive infinity, my graph is always below the x-axis, so my graph is decreasing, meaning you're coming down off of that caffeine high. So my graph is decreasing. All right, how long does it take for the caffeine level to reach its peak? Well, it takes, is this in hours? I don't remember what this was, hours. It takes 1 hour, 1.19 hours to reach it. So it reaches its peak when it stops increasing. So that 1.19 hours. So let's say reaches its peak. .19 hours. Remember, it's increasing, it's increasing. You drank your energy drink, you're feeling good, and then, it hits you, and you start coming down. And that's why the slope is negative down here. It's coming down. All right. That was just kind of a practical one. Pretty good one. All right. Example 26. How are we doing on time? Oh, of course I was hoping this would be shorter, y'all. Sorry. These are all cognitive problems, and most of them are off of your homework that you're doing too. I think I tried to pull most of them. In fact, I don't even know if I did homework on this one. That was different from what we did here. All right. For the function f, you are given f prime of x equals 4x minus x squared. That's this right here. The function f is decreasing on the interval from k to infinity. Find the smallest possible value for k. All right. So, we are negative down here. We are negative down here. These are decreasing. And then this one up here, we are a positive slope. Right? Because this is f prime of x. So there it is. So let's label what we know. We know this is a turning point here at 0. This is a turning point right here. For the function f, you're given this. We labeled it. The function is decreasing on an interval. Which interval are we decreasing? We are decreasing down here from negative infinity to 0. And we're decreasing from 4 to infinity. So let's write that. We're decreasing from negative infinity to 0. And we're decreasing from 4 to positive infinity. Find the smallest possible value of k. Oh, well, here it is. What interval would that be? What would k be? K would be 4. K is where it's decreasing. If I wanted to say where it's increasing, I would say from 0 to 4, we are increasing. That's when my derivative is positive. All right. The diagram shows the graph of y equals f prime of x. So again, this is the derivative. Sketch the possible graph of f of x. Okay. So you're going to look at when is the graph above the x-axis. So we are positive here. And we are positive here. We are negative down here. And we are negative here. 3 turning points. It turns at 0. It turns at 1, and it turns at 4. All right, so I'm going to put some dashed lines here. It helps me when I do these. These are my turning points. All right, I'm going to give you a second to kind of sketch it how you think it might look. Our graphs will probably not match, but they will be similar in what they do. Remember, when it's pink, it's positive. I don't know if y'all caught that. That's why I did pink for positive. I have a turning point at 0, so I'm going to put a turning point right here. I have a turning point at 1. I'll put a turning point about right there. And then I have another turning point at 4, and I'll put it up here. So, during the pink time, this side over here, my graph is increasing. It's growing. So I'm going to say it's growing. But then during this interval, my graph is decreasing. So my graph is decreasing. During this interval, my graph is positive. It's growing. It's increasing. So maybe it looks like that. And then from here over to the end, it's decreasing. So maybe it goes like that. That is a possible graph. Notice that's straight. I don't know what the graph is doing, but that is a possible sketch of what it could look like. All right, on to the next one. Example 28. All right, I know this one's straight out of Cognitive. I remember doing it. Okay, the diagram shows a picture of Kyrie Irving shooting a free throw. Maybe that's a famous basketball player, I don't know. The distance of the coordinate axis are meters. Okay, so these are meters. The equation of the ball y equals f of x for some function f. The derivative of the function is given by this. So this is the function f prime of x. What are the horizontal distance of the ball from the center of the hoop, from the y-axis, when the ball is at the highest position? Give your answer in meters rounded to 3 sig figs. All right, give you a second to kind of look at that. All right, so let's see. We're kind of looking at, we're kind of looking at this, and we want to know the horizontal distance. I'm going to mark this again. So the distance of the coordinate axis are where am I at? That's not where I wanted. The derivative of the function is given by this. Find what is the horizontal distance from the center of the hoop of the y-axis when the ball is at its highest point. Give the answer in meters. Okay, I was kind of looking at what I did on this. Okay. So here's my function. I want to know this distance from here, and then I'm going to kind of do this right here. I don't think that's that right there exactly. What I'm trying to find is the horizontal distance. I'm trying to find this distance right here from this line to the center of the hoop. And they're saying that this, they didn't draw it very good, but they're saying that this is the maximum height of the ball. So he shot the ball, or, you know, I guess it's really over there. If I want to know the maximum height, I want to know when the ball is right up here. And at that point right there, I'm going to draw it in pink, but maybe I shouldn't. When the ball is at the maximum height, the slope of the tangent, the derivative, wouldn't it be 0 at the maximum height point? So I kind of want to think about this like this. I want to know, when does this equal 0? Because that's going to be the slope of this line at the maximum point. And then from that point, I want to know the horizontal distance. I guess my horizontal line was a little bit off. Wasn't really at the right spot. So I want to know the distance from right here to right here. What's the x value? Because if I can find the x value, that'll give me my point. So let's figure out what's 0. When is y 0? So I want to know, when is f prime of x 0? So 0.946 minus 0.457x. When does that equal 0? Well, let's just solve. I mean, that's basic algebra, right? So I'm going to say x equals 0.946 divided by 0.457. I'm going to do 3 sig figs when I do that. I got 2.0700. All right, so what does that mean? Doesn't that give me the x value right here? 2.07. So at 2, I was pretty close when I drew it that time. 2.07 this way, that's where the slope of the tangent line is 0. So what's the horizontal distance? 2.07. And it was meters. All we had to do was find the slope of the tangent line at 0. When is it 0? It's 0 when x is 2.07. If x is 2.07, this horizontal distance is where the slope is 0. So the horizontal distance to the center of the hoop is 2.07. All right. And 29. Where's that at? There it is. Find the number of stationary points for the graph y equals 1/2 x to the 4th minus 2x to the 3rd. Oh, I already did that one. Minus 4x squared plus 11. Okay, stationary points. Turning points. We just want to know the turning points. So let's take the derivative of this so we can figure out the turning points. Y prime equals, and I'm going to give you a second to do that. If you've watched the other videos, you know you're going to multiply and reduce the exponent by 1 to find the derivative. All right, half of 4 is going to be 2, and I'm going to reduce x to the 4th and make it the 3rd. 3 times 2 is going to be 6. Reduce 3 by 1, it'll be squared. 2 times 4 will be 8. And I'm going to reduce that x squared to just x. And the 11, derivative of a constant, is 0. Okay, so there's my prime. I want to know, if I were to graph that, and I could graph it, I want to know how many turning points does it have. So what I'm going to do is I'm going to factor this, and I'm going to try and figure it out. Now, there are 2 ways to factor it. Algebra people, you are going to factor out an x. So here we go. Let's do y prime equals factor out of x, and you are going to, actually 2x. You're going to have x squared minus 3x minus 4. And then you're going to say 2x, and you're going to factor that. My least likely algebra people, we are going to use our calculator. And we are going to go to the App Store, and we're going to do the polynomial solver. We're going to go here. We want to know the polynomial root finder. We have a degree 3. And then we're going to go next. We're going to plug in what we have. We have 2. Enter, enter. We have -6. Enter, enter. We have 8. Enter, enter. And we have 0. Enter. And then we're going to tell it to solve it. And why did it not solve? Oh, did I do solve? 2 -6x squared. Okay, that's an interesting one. It should have solved it a little better than that. Okay, over here, if I'm doing this, and we'll see, maybe there's, I don't know why it didn't solve this. I'm going to go back and look at that and see why. And in class, I will be able to tell you why that did not solve. -4 and 3, so I'm going to do 4 and 1. I'm going to do -4 and +1. There's all my factors. So I set y prime. I'm going to set each of those equal to 0 because every time each one of these is 0, that's going to be my turning point. So I'm going to do 2x equals 0, x minus 4 equals 0, and x plus 1 equals 0. And these are going to give me my turning points. So this is going to give me x equals 0. This is going to give me x equals 4. And this is going to give me x equals -1. All right, let me pull that up just a little bit. So if I were to graph it, I basically have find the number of stationary points on this graph. Well, it looks to me like I'm going to have 3 stationary points. I have one at 0, one at 4, and one at -1. So I have 3 stationary points. Now, just to make sure we understand what's going on stationary points. At 0, I have 1. At 4, I have 1. And at -1, I have a stationary point. Okay? So I'm trying to think which way I want to do this. I could graph this in my calculator if I wanted to. Let's see. I forget, when you get in that polynomial solver, it gets really hard to get out of it. If I graph the derivative, let me graph the derivative because I feel like that's actually easier to do. 2x to the third minus 6x squared minus 8x. Oh my goodness, really? Okay, 2x to the third minus 6x squared minus 8x. Okay, now I'm going to graph it. Okay, so here's what it looks like, right? So I'm going to go here. So it's going up here. At 1, it turns and it does this. And then it comes down and then it goes up. All right. So it's got a negative slope. Remember, when it's negative, we're down here. Up here, we're positive. It's increasing. When we're below the x-axis, we're decreasing. And then up here, we are increasing. If I were to sketch a rough graph, I know that these are here. These are my turning points. Okay, so I'm going to put 1, I'll put 0, and I'll put 4. I have no idea what this graph looks like. But I know it's decreasing, so it's coming down here to here. I guess I should have done it. And then it starts increasing, so I guess I should have put this one up here. Then it starts increasing to here. And then during this interval from 0 to 4, it's decreasing. It's got a negative slope. And then it comes back up for forever this way. So my graph looks something like that if I were to graph it in my calculator. And I could have just graphed it in my calculator. I don't even want to try and put all that in. That's a hot mess. 1/2 x to the 4th minus 2. I don't know. All right. So those of you that solved it algebraically, that's how you would do it there. I am going to take just a second if you want to keep watching. Otherwise, I think we're done, right? Yes, you're you know everything. If you've done all of this, all of the cognitives should work. I just want to look at this, those of you that were doing the polynomial solver, and we'll problem shoot here together. I'm going to say 1. We did 3. We did real. We wanted auto. We did normal. And we did degrees. Yeah, we were in degrees. So we did next. We did 2x to the third minus 6x squared plus 8x plus 0 equals 0. Why did that not work? Solve. Store, coefficient, make. There were 3 solutions on that. We got 0, 4, and -1. I'm not sure. Polynomial root solver. Let's go there. Polynomial root finder help. Set up a made polynomial. Input the coefficients. Press solve. Press mode to change the setting. Okay. Real. Okay, let's go back. Real type not available for degrees greater than or equal to 4, which we didn't need that. Clear coefficients, load coefficients, list, solve, calculate the roots. Polynomial y equals. Okay, we should be good. Okay, let's second quit. Okay, so let's go to the apps. Actually, I'm going to do second plus 712 because sometimes, your calculator gets all messed up. And maybe yours worked and mine didn't. So I'm going to do 9, and then I'm going to do the polynomial root finder of the 3rd degree. Move that over to 3rd. Next. 2, enter, enter, -6, enter, enter, 8, enter, 0, enter, enter, solve. Oh my gosh, why do I keep getting 0? Okay, I don't know. I don't know.
All right, y'all. Well, maybe by the time we teach it in class, I'll figure out what's going on with my polynomial root solver. It should give me all of them. I don't know why. 2x squared. Load? No, I don't want to load. Solve. Okay, well, I'm going to keep. Yeah, we found the real ones. I don't know what float means. Okay, well, I don't know. I hope this helped y'all, and I didn't hinder y'all too much trying to figure that out. Have a good day.
Okay, so I'm going to attach this on because I realized after I looked at this, when I did the polynomial root finder, and I did next, I had the wrong value for A in there. So if you hit there and you hit solve, you should get those, which is the exact same we got here. Algebra people, you can factor. Those that prefer the calculator, you can just do the polynomial root finder. That gives you your zeros, which are your stationary turning points, and bam, you are done. I just wanted to go back and show y'all that.